Abstract. Contemporary leadership operates within increasingly complex, data rich, and technologically mediated environments that demand new cognitive capabilities. Computational thinking, a problem solving approach rooted in decomposition, pattern recognition, abstraction, and algorithmic reasoning, has emerged as a critical competency for leaders navigating digital transformation, operational complexity, and strategic uncertainty. This article examines the organizational and individual consequences of computational thinking deficits in leadership, drawing on empirical research from management science, information systems, and organizational behavior. Evidence demonstrates that leaders who apply computational thinking frameworks achieve superior strategic outcomes, foster more adaptive organizational cultures, and make more effective data informed decisions. The article synthesizes evidence based interventions organizations can deploy to develop computational thinking capabilities among leaders, including structured problem decomposition training, cross functional immersion experiences, algorithmic literacy programs, and systems modeling practices. Real world examples from healthcare, financial services, manufacturing, and technology sectors illustrate successful implementation approaches. The article concludes with forward looking recommendations for embedding computational thinking into leadership development ecosystems and organizational learning architectures. Introduction. The leadership landscape has fundamentally shifted. 21st century executives confront problems characterized by unprecedented scale, velocity, and interconnectedness. From orchestrating global supply chains affected by geopolitical disruption, to interpreting complex customer behavior patterns across digital channels, to navigating the organizational implications of artificial intelligence deployment. Davenport and Ronenke, 2018. Traditional leadership frameworks emphasizing interpersonal influence, strategic vision, and financial acumen remain necessary, but insufficient for this new reality. Computational thinking offers leaders a structured cognitive toolkit for tackling complexity. Originally articulated by Seymour Papert in the 1980s and popularized by Jeanette Wing, 2006, computational thinking encompasses the mental processes involved in formulating problems, so their solutions can be represented as computational steps and algorithms. While initially associated with computer science education, scholars increasingly recognize computational thinking as a fundamental literacy for professionals across disciplines. Grover and P., 2013. For leaders specifically, computational thinking manifests not as coding proficiency, but as a disciplined approach to problem solving, breaking complex challenges into manageable components, identifying patterns across seemingly disparate situations, creating simplified models that capture essential dynamics while filtering noise, and designing systematic processes to achieve repeatable outcomes. Research suggests leaders who think computationally demonstrate enhanced capabilities in strategic planning, operational improvement, digital transformation, and innovation management. Romero et al., 2017. The practical stakes are considerable. Organizations led by computationally fluent executives report faster adaptation to technological disruption, more effective data utilization, and stronger innovation performance. Brynjolfsson and McElherin, 2016. Conversely, leadership teams lacking these capabilities struggle to extract value from digital investments, often defaulting to intuition based decision making even when superior data driven approaches exist. As one McKinsey study found, only 8% of organizations successfully scale digital and analytics initiatives beyond pilot stages, a failure often attributed to leadership's inability to think systematically about technology enabled transformation. Bussey et al., 2016. This article examines why computational thinking has become essential for modern leadership, what happens when leaders lack this capability, and how organizations can systematically develop it across their leadership populations. The computational thinking landscape. Defining computational thinking in leadership contexts. Computational thinking comprises four interconnected cognitive processes, each with distinct leadership applications. Decomposition involves breaking complex problems into smaller, more manageable subproblems. For leaders, this means dissecting strategic challenges, such as improving customer retention, into constituent elements: acquisition quality, onboarding effectiveness, product market fit, service recovery, engagement cadence, that can be addressed independently and systematically. Wing, 2006. Pattern recognition entails identifying similarities, commonalities, or regularities across different contexts. Leaders who recognize patterns can transfer solutions across business units, anticipate emerging challenges by detecting early signals, and avoid reinventing approaches to recurring problems. Grover and P. 2013. Abstraction requires filtering out irrelevant details to focus on essential features. Computationally literate leaders distinguish signal from noise in complex data environments, build simplified models that capture key dynamics, and communicate complex ideas through parsimonious frameworks. Angeli et al., 2016. Algorithm design means creating step by step procedures to solve problems. In leadership practice, this translates to developing systematic processes for decision making, standardizing best practices into repeatable workflows, and designing governance mechanisms that produce consistent outcomes across variable conditions. Barr and Stephenson, 2011. Critically, computational thinking differs from traditional analytical thinking in its emphasis on process over outcome. While analytical thinking focuses on deriving correct answers through logical reasoning, computational thinking emphasizes designing systematic approaches that can be automated, scaled, and continuously improved. Capabilities increasingly vital in technology mediated organizations. Denning, 2017. State of practice, computational thinking adoption in leadership. Despite growing recognition of computational thinking's importance, empirical evidence suggests significant capability gaps among current leadership populations. A survey of 1,200 executives across Fortune 1000 companies found that while 87% acknowledged the importance of thinking algorithmically about business problems, only 23% felt confident applying computational thinking frameworks in their work. Bharadwaj et al., 2013. This gap appears particularly pronounced among executives who established their careers before the digital era. Research indicates leaders who entered the workforce after 1990 demonstrate measurably stronger computational thinking capabilities, likely reflecting greater exposure to digital technologies during formative career stages. Kane et al., 2015. However, even digitally native leaders often struggle to translate personal technological fluency into systematic organizational problem-solving approaches. Several factors contribute to this capability deficit. Educational background limitations. Most executive education traditionally emphasized case-based reasoning and frameworks rooted in industrial-era management rather than computational problem-solving approaches. Schoemaker et al., 2018. Professional specialization effects. Leaders rising through functional tracks, finance, marketing, operations, often develop deep domain expertise without acquiring cross-disciplinary computational thinking skills. Tushman and O'Reilly, 2013. Organizational culture barriers. Many established organizations reward decisive action and intuitive judgment over systematic, process-oriented problem decomposition, creating disincentives for computational thinking adoption. Davenport and Harris, 2017. Time pressure constraints. Executives facing constant decision demands may default to heuristic-based approaches rather than investing time in structured problem decomposition, even when systematic approaches would yield superior outcomes. Kahneman, 2011. The distribution of computational thinking capabilities varies significantly across industries. Technology, financial services, and healthcare sectors show higher leadership adoption rates, driven by regulatory requirements, competitive dynamics, and operational complexity that necessitate systematic approaches. Traditional manufacturing, retail, and professional services exhibit lower adoption, though digital disruption is accelerating capability development across all sectors. Westerman et al., 2014. Organizational and individual consequences of computational thinking deficits. Organizational performance impacts. When leadership lacks computational thinking capabilities, organizations experience measurable performance degradation across multiple dimensions. Digital transformation failure. Research examining 1,800 digital transformation initiatives found that projects led by executives with strong computational thinking skills achieve success rates 2.6 times higher than those led by executives lacking such capabilities. Fitzgerald et al., 2014. Leaders who cannot decompose transformation challenges into manageable work streams, recognize patterns across implementation contexts, or design systematic change processes struggle to coordinate complex technology enabled initiatives. Analytics underutilization. Organizations invest heavily in data infrastructure and analytics capabilities, yet studies consistently show 60 to 73% of enterprise data goes unused in decision making. Laval et al., 2011. This gap stems partly from leadership's inability to think computationally about how data can inform systematic processes rather than merely supporting ad hoc decisions. Executives who lack abstraction skills cannot identify which metrics truly matter. Those who cannot think algorithmically struggle to embed insights into operational workflows. Innovation stagnation. Computational thinking enables leaders to systematically explore solution spaces, test assumptions through rapid experimentation, and scale successful approaches. Research demonstrates that organizations whose executives apply computational thinking frameworks generate 40% more patent applications and bring new products to market 35% faster than those relying on traditional innovation approaches. Brynjolfsson and McElherin, 2016. Without these capabilities, innovation efforts remain chaotic, resource intensive, and difficult to replicate. Operational inefficiency. Leaders who cannot decompose complex operational processes struggle to identify improvement opportunities systematically. A study of manufacturing operations found that facilities led by computationally literate plant managers achieved 18% higher productivity than comparable facilities. A difference attributed to systematic process decomposition, pattern recognition across production runs, and algorithmic optimization. Bloom et al., 2012. Strategic misalignment. Computational thinking helps leaders create clearer connections between high level strategy and operational execution by breaking strategic objectives into measurable components and designing systematic approaches to achieve them. Research shows organizations whose executives demonstrate strong computational thinking capabilities report 31% higher strategy execution effectiveness scores. Sull et al., 2015. Individual stakeholder impacts. Computational thinking deficits in leadership create consequences that cascade to employees, customers, and other stakeholders. Employee experience degradation. When leaders cannot think systematically about workflow design, employees face poorly structured processes, unclear decision rights, and inefficient coordination mechanisms. Survey research indicates employees working under computationally literate managers report 28% higher job satisfaction and 22% lower role ambiguity than those reporting to managers lacking such capabilities. Colbert et al., 2016. Customer experience inconsistency. Leaders who cannot design algorithmic approaches to service delivery struggle to ensure consistent customer experiences across touchpoints and interactions. This inconsistency drives customer frustration. Research demonstrates that experience variability predicts customer churn more strongly than average experience quality. Dixon et al., 2010. Stakeholder trust erosion. In sectors like healthcare and financial services, stakeholders increasingly expect organizations to make evidence based, systematic decisions rather than relying on intuition or precedent. Leaders who cannot articulate clear, logical processes behind consequential decisions face growing skepticism from regulators, patients, customers, and communities. Schaffer and Shelley, 2020. Career development limitations. Employees working under leaders who lack computational thinking skills miss opportunities to develop these capabilities themselves. Given that computational thinking increasingly predicts career advancement in technology mediated organizations, this creates development gaps that compound over time. Ananiadou and Claro, 2009. Evidence based organizational responses. Organizations have deployed various interventions to develop computational thinking capabilities among their leadership populations. The following approaches show strong empirical support. Structured problem decomposition training. Training programs that explicitly teach leaders to decompose complex problems into manageable components demonstrate measurable impact on decision quality and strategic effectiveness. These programs typically combine conceptual frameworks with hands-on practice using real organizational challenges. Effective problem decomposition training incorporates several elements. Diagnostic frameworks that guide leaders through systematic problem structuring, issue trees, logic trees, hypothesis driven approaches. Facilitated practice sessions, where leaders apply decomposition techniques to current business challenges with expert coaching. Peer learning structures that enable leaders to observe and critique each other's decomposition approaches. Post training reinforcement through job aids, decision templates, and periodic refresher sessions. Procter & Gamble embedded problem decomposition training into its leadership development curriculum in 2012, teaching executives to apply structured frameworks when addressing complex business challenges. The program emphasizes breaking broad questions, such as how do we accelerate growth in emerging markets, into specific, testable hypotheses and actionable work streams. Internal assessments found that business units led by executives who completed the training achieved 16% faster problem resolution times and developed more comprehensive strategic plans than control groups. Martin and Uchner, 2012. The training particularly improved leaders' ability to identify dependencies across subproblems and sequence initiatives effectively. Cross-functional technology immersion. Immersive experiences that expose leaders to technology development processes build intuition for computational problem-solving approaches. These programs place executives in engineering or data science teams for extended periods, enabling firsthand observation of how technical professionals decompose problems, recognize patterns, create abstractions, and design algorithms. Successful technology immersion programs share common characteristics. Meaningful duration, typically 2 to 8 weeks, allowing genuine integration into technical workflows rather than superficial exposure. Active participation requirements, where leaders contribute to real technical work rather than passively observing. Structured reflection processes that help leaders extract transferable insights applicable to their leadership contexts. Senior sponsorship ensuring organizational support and removing barriers to executive participation. Capital One pioneered executive technology immersion in 2015, requiring all senior leaders to complete multi-week rotations working alongside software engineering teams. Participants pair program with developers, attend sprint planning sessions, and contribute to actual code bases. This hands-on involvement helps leaders understand how engineers think about problem decomposition, modularity, abstraction, and systematic testing. Follow-up research found that leaders who completed immersion rotations demonstrated 34% improvement in their ability to have substantive technical conversations, made more realistic technology investment decisions, and fostered stronger engineering cultures in their units. Davenport and Bean, 2018. Algorithmic literacy and process modeling. Training leaders to understand algorithms and model business processes as systematic procedures enhances their ability to design scalable, repeatable solutions. These programs don't require leaders to become programmers, but rather to understand algorithmic thinking principles and apply them to organizational challenges. Effective algorithmic literacy initiatives include conceptual grounding in fundamental algorithmic concepts, sequence, selection, iteration, recursion, using business-relevant examples. Process mapping exercises, where leaders diagram current workflows and redesign them using algorithmic thinking principles. Automation opportunity identification training that helps leaders recognize which processes would benefit from systematic standardization. Decision algorithm design practice creating explicit decision rules and criteria for recurring organizational choices. Cleveland Clinic implemented algorithmic literacy training for clinical and administrative leaders in 2016, teaching process modeling and systematic workflow design. Participants learned to map patient care pathways, identify variation sources, and design standardized protocols that improved outcomes while preserving necessary clinical judgment. Leaders applied these skills to challenges ranging from emergency department throughput to surgical scheduling. The initiative contributed to 23% reduction in care pathway variability and 19% improvement in patient flow metrics across participating departments. James and Savitz, 2011. Leaders reported that process modeling skills helped them communicate more effectively with both clinical staff and IT teams implementing workflow technologies. Data-driven decision-making frameworks. Programs that teach leaders systematic approaches to incorporating data into decisions build computational thinking capabilities while improving decision quality. These frameworks emphasize pattern recognition, abstraction, distinguishing signal from noise, and algorithmic consistency in decision processes. Key components of effective data driven decision training include metric definition workshops teaching leaders to identify leading indicators and design measurement systems aligned with strategic objectives. A/B testing methodologies demonstrating systematic approaches to testing hypotheses and learning from experiments. Dashboard design principles helping leaders abstract essential information from complex datasets. Decision logging practices encouraging leaders to document decision criteria and systematically review outcomes. Booking.com developed a comprehensive data driven decision making curriculum for leaders at all levels, emphasizing experimentation, metric driven evaluation, and systematic learning. The program teaches leaders to formulate testable hypotheses, design controlled experiments, interpret statistical results, and institutionalize successful practices. This computational approach to decision making helped Booking.com achieve industry leading optimization capabilities. The company runs over 1,000 simultaneous A/B tests and makes dozens of data informed decisions daily. Kohavi and Tomk, 2017. Leaders trained in the framework demonstrate measurably stronger pattern recognition capabilities, identifying opportunities to apply successful approaches across different contexts. Systems thinking and modeling capabilities. Training leaders to understand and model complex systems, recognizing feedback loops, delays, nonlinearities, and emergent properties. Develops sophisticated computational thinking capabilities applicable to strategic challenges. Systems modeling helps leaders abstract essential dynamics, recognize patterns across different organizational contexts, and anticipate unintended consequences. Comprehensive systems thinking development includes causal loop diagramming teaching leaders to map feedback structures driving organizational dynamics. Stock and flow modeling helping leaders understand accumulation processes and resource constraints. Simulation exercises using system dynamics software to test strategic assumptions and explore scenario implications. Mental model surfacing techniques that make implicit assumptions explicit and testable. Shell has employed systems thinking approaches in leadership development since the 1990s, teaching executives to model complex strategic challenges as dynamic systems. Leaders learn to identify reinforcing and balancing feedback loops, recognize leverage points, and anticipate delayed effects of strategic decisions. Shell's scenario planning process, built on systems thinking principles, helped the company navigate industry disruptions more successfully than competitors. Internal research found that business units led by executives with strong systems thinking capabilities achieved 27% higher strategic forecast accuracy and made more resilient long-term investment decisions. Senge, 1990. Van der Heijden, 2005. Building long-term computational thinking capacity. While targeted interventions build discrete capabilities, sustainable computational thinking development requires embedding these competencies into organizational DNA through systemic changes. Integration into leadership development architectures. Organizations must redesign leadership development programs to treat computational thinking as a core competency rather than a specialized technical skill. This integration involves several shifts. Curriculum redesign. Leadership development programs should incorporate computational thinking modules throughout rather than treating them as standalone technical add-ons. Harvard Business School, for example, now integrates algorithmic thinking, data analytics, and systems modeling across its core MBA curriculum rather than confining these topics to elective courses. Davenport, 2014. Assessment evolution. Leadership selection and promotion processes should explicitly evaluate computational thinking capabilities alongside traditional leadership competencies. This requires developing valid assessment methods, case studies requiring problem decomposition, simulations testing pattern recognition, or structured interviews probing algorithmic reasoning capabilities. Mentorship matching, pairing emerging leaders with mentors who demonstrate strong computational thinking skills accelerates capability transfer. Organizations can systematically identify computationally literate senior leaders and create structured mentorship programs focused on developing these capabilities in high potential talent. Rotational assignments. Career paths should include rotations that build computational thinking, such as process improvement projects, analytics team assignments, or technology transformation initiatives, particularly for leaders identified as succession candidates for senior roles. Cross functional collaboration structures. Computational thinking develops most effectively through repeated exposure to diverse problem solving approaches. Organizations can design structural mechanisms that facilitate such exposure. Multidisciplinary project teams. Forming teams that combine business leaders, technologists, data scientists, and operational experts creates natural learning environments. When leaders work alongside professionals who think computationally by training, they internalize these approaches through observation and collaboration. Communities of practice. Organizations can establish forums where leaders share experiences applying computational thinking to business challenges, critique each other's approaches, and collectively refine techniques. These communities accelerate diffusion of effective practices across the organization. Decision review processes. Implementing structured decision reviews where leaders present their problem decomposition, pattern analysis, and algorithmic reasoning creates accountability for computational rigor while providing learning opportunities for observers. Reverse mentoring programs. Pairing senior executives with early career employees who possess strong computational thinking skills, often reflecting recent educational experiences, enables bidirectional learning that benefits both parties. Embedded learning systems and knowledge management. Organizations can build computational thinking capabilities by creating systems that capture, codify, and disseminate effective problem solving approaches. Decision templates and frameworks. Developing standardized templates that guide leaders through computational problem solving processes creates scaffolding for consistent application. These might include problem decomposition worksheets, pattern analysis frameworks, or algorithm design canvases. Case libraries, building searchable repositories of past problems, decomposition approaches, and solutions enables pattern recognition across organizational contexts. Leaders facing new challenges can identify analogous situations and adapt proven approaches rather than starting from scratch. Process mining and analysis. Technologies that automatically analyze operational data to identify process patterns, bottlenecks, and optimization opportunities help leaders develop stronger pattern recognition capabilities while improving operations. Real-time decision support. Intelligent systems that provide relevant data, suggest analytical approaches, and highlight patterns during decision-making serve both as performance aids and as continuous learning mechanisms. Organizations like Amazon exemplify this approach through their mechanisms, systematic processes, and tools that embed computational thinking into daily operations. Amazon's narrative memo format forces leaders to decompose complex proposals into logical components. The working backwards process requires algorithmic specification of customer experiences, and automated metrics dashboards make pattern recognition accessible to all leaders. Stone, 2013. These mechanisms simultaneously improve decision quality and continuously reinforce computational thinking skills across the leadership population. Cultural reinforcement and normative change. Ultimately, computational thinking becomes embedded in leadership practice only when organizational culture values and rewards these approaches. Leadership modeling. Senior executives must visibly demonstrate computational thinking in their own decision making, explicitly discussing how they decompose problems, recognize patterns, create abstractions, and design systematic processes. This top down modeling signals the importance of these capabilities. Recognition systems. Organizations should celebrate and reward leaders who exemplify computational thinking, highlighting cases where systematic problem decomposition led to breakthrough solutions or where algorithmic approaches generated measurable improvements. Vocabulary development. Creating shared language around computational thinking concepts helps normalize these approaches. When leaders routinely discuss decomposing this problem, recognizing patterns across these situations, or designing an algorithm for this decision, computational thinking becomes part of organizational discourse. Failure tolerance for systematic experiments. Computational thinking often involves disciplined experimentation and learning from failures. Organizations must create psychological safety for leaders to test hypotheses, acknowledge when approaches fail, and systematically iterate toward better solutions rather than punishing experimental failures. Conclusion. Computational thinking has transitioned from a specialized technical competency to a fundamental leadership capability in technology mediated, data rich organizations. Leaders who can systematically decompose complex problems, recognize patterns across diverse contexts, abstract essential features from noisy environments, and design algorithmic approaches to recurring challenges, achieve superior strategic outcomes, drive more effective digital transformations, and build more adaptive organizations. The evidence base is clear. Computational thinking deficits in leadership create measurable performance consequences, from digital transformation failures to analytics underutilization to innovation stagnation. Conversely, organizations that systematically develop these capabilities through structured training, immersive experiences, process modeling education, data driven decision frameworks, and systems thinking development demonstrate improved strategic execution, operational efficiency, and competitive positioning. Building computational thinking capacity requires more than episodic training interventions. Sustainable capability development demands integration into leadership development architectures, creation of cross functional collaboration structures, implementation of embedded learning systems, and cultural shifts that value systematic problem solving approaches. Organizations that successfully make these investments position their leadership populations to navigate the complexity, uncertainty, and technological change that define the contemporary business environment. For individual leaders, developing computational thinking skills represents a career imperative. As organizations become increasingly technology enabled and data driven, leaders who lack these capabilities face growing disadvantages, struggling to communicate with technical teams, unable to extract value from digital investments, and ill equipped to design the systematic processes that modern organizations require. The good news is that computational thinking can be learned at any career stage through deliberate practice, exposure to diverse problem solving approaches, and systematic reflection on one's own thinking processes. The question facing organizations is not whether to develop computational thinking capabilities among leaders, but how quickly and systematically to do so. In an era where competitive advantage increasingly derives from superior execution of technology enabled strategies, the organizations that move decisively to build these capabilities will shape their industry's futures, while others struggle to adapt.